Welcome back everyone to 1.6. This is the final video. We're going to be considering the third and final and probably most important case, which is what happens when you have 0 divided by 0, right? And we're going to need to apply a lot of algebra to these limits. So the objective, right? We're going to go ahead and recall some old algebraic techniques, which seemed just like punishment back then, but they actually have wonderful uses, right? So things like factoring and multiplying by a conjugate. We're going to use these then to calculate a variety of limit problems. Okay, so the first thing I need to tell you a little bit about a theorem here. I call this a cancellation theorem, but really we can do it for all sorts of things like multiplying by conjugates and whatnot. So it says that if you have two functions that are mostly equal to each other, they're equal to each other whenever x is not equal to a, then the claim is that the limit as x approaches a of f of x will be equal to the limit as x approaches a of g of x. Again, because limits really don't care about what's happening at a. All right, so let's go ahead and try to solve this here. First example, limit as x approaches 1 for this rational function. Well, as we saw before, I want to see, can I use the direct substitution property? The direct substitution property says, well, let's go ahead and plug in 1 and see what happens. So if I go ahead and plug in 1, let's see, in the top I would get 1 squared. Let's see, 2 times 1 minus 3. In the bottom I would get 1 squared minus 1. So notice in this case you get 0 over 0. All right, so this is telling me I can't just use the direct substitution property. And I'm not getting a vertical asymptote as far as I can tell, right? It's not something non-zero divided by 0. And so the question is, how do these zeros cancel, right? Is the answer just 1? Probably not, right? So how do I get these zeros to cancel? And this is where we need to use these techniques. So when I look at this here, I see polynomial over polynomial. I'm leaning towards factoring. I'm going to ask myself, what happens if I was to factor this, right? And so if I factor it, limit as x approaches 1. Let's see, the numerator can be factored into an x plus 3 and an x minus 1. And the denominator can be factored into an x plus 1, x minus 1. So we need to be really good at our algebra skills. And here's where I'm going to use this cancellation law, right? That I'm going to go ahead and just cancel these. And notice this is actually the problem right here. When I plugged in 1, I got out 0 on the top and 0 on the bottom. And it's because of these terms, right? Because 1 minus 1 would be 0. 1 minus 1 would be 0, right? So that's what's giving me the 0 on the top and bottom. So this is how we're going to cancel those zeros, essentially. Now, again, because of this theorem up here, we know that when I do this cancellation, the limit is the same, right? That I haven't fundamentally changed the limit by any means. Now I have this thing. And the question is, okay, maybe I can use direct substitution now. So if I use direct substitution and plugged in 1 everywhere I saw an x, I would have 4 divided by 2, which would happen to be 2. And that is my final answer. So notice, kind of the first time people see this, they see 0 divided by 0, they say, they perfectly cancel and they equal 1. That was not the case, and in fact, it's very rarely the case. You really have to, kind of solve this all out using your algebra to figure out how these weird zeros cancel. Okay, let's try another one here. Evaluate the limit if it exists. The limit as x approaches 2. Oof, it's a fairly complicated one. Let's see what's going on here. So again, I'm going to use the direct substitution property, see what happens. So if I was to plug in a 2 everywhere I see an x, I would have 1 divided by 2 minus 1, subtract away 1, all divided by 2 minus 2. So in the top, I would have 1, so 2 minus 1 is 1, so I'd have 1 minus 1 divided by 2 minus 2 is 0. So in this case, I have 0 divided by 0. So I'm in this case, right? This 0 over 0 case, I'm hoping that I can employ some algebra to try to get things to cancel out. Again, so plugging in the 2 everywhere I see an x kind of tells me which case I'm in. Maybe I'm just in this direct substitution case, right? And it's very easy. Or if I'd gotten a non-zero divided by 0, then I would know that I'm thinking about vertical asymptotes. But because I get 0 over 0, I know that I'm thinking, I'm looking for something to cancel. Okay, so when I look at this problem, I see all these fractions over fractions, all these terms, right? And I'm thinking, okay, right, there's all these denominators, numerators. What if I tried to get common denominators, right, with all these fractions around? So in this case, the algebra technique that I'm going to try to use, and actually it'll help us a lot, is I'm going to try to get a common denominator. Let's go for it. So the limit as x approaches 2, let's see, instead of dividing by this x minus 2, let me go ahead and multiply by its reciprocal. I'm going to move it out here. So that'll be my first step. That way it looks a little bit nicer. And then with this right here, we have a couple of fractions that are trying to communicate with each other, trying to subtract away. So whenever you have fractions who are trying to add or subtract, right, getting a common denominator, like I said, is a good technique. So let's go ahead and do that. Let me go ahead and write then, let's see, the common denominator should be x minus 1, so I'm going to go ahead and multiply this one right here. Let me go ahead, this 1 right here. X minus 1 on top and on bottom. And so this is going to give me 1 minus x minus 1, all divided by x minus 1, right? I have that common denominator now. And notice that you have to be careful. You subtract away this entire bit right here, right? You need to subtract away all of it, so I'm including the parentheses. If you forget to include these parentheses and you only subtract away the x and you forget to subtract away this negative 1, you're going to get the wrong answer. Okay. Next up, limit as x approaches 2 of 1 over x minus 2. And let's see, we have 1 minus x minus a negative 1. So this is, I'm going to go ahead and combine this. The 1 and the minus a negative 1 is going to become 2 minus x over x minus 1. And now I'm close, right? This looks almost like this should cancel with each other. They're very close to each other, but they're just off by a little bit. So I'm actually going to go ahead and multiply both the numerator and the denominator here by by negative 1. And so long as I do it to both the numerator and the denominator, the claim is I haven't fundamentally changed anything. Okay, so limit as x approaches 2, 1 over x minus 2. And let's see, when I multiply by negative 1, right, you may be asking, why am I doing this? Well, negative 1 times negative x is going to be x. Negative 1 times 2 is going to be negative 2. And now notice that these perfectly line up. I'll do the same thing over here, 1 minus x. And so these things actually cancel, right? And I've been looking for them to cancel because if I plugged in 2, right, this gives me the 0 in the denominator, this gives me the 0 in the numerator. So I've canceled out my zeros. I've successfully gotten those zeros to cancel out to some extent. Again, I'm using this cancellation property that says that it's okay to cancel these and you don't kind of fundamentally change the limit. So now, all I'm left with is this. Let's try direct substitution again. So if I plug in 2 everywhere I see an x, I would get 1 over 1 minus 2, 1 over negative 1, which simplifies down to negative 1. So in this case, my 0 over 0 is canceled and gave me negative 1. All right, so that's kind of the second big algebra thing that we need to remember, right? So the first one was factoring, the second one is getting a common denominator, and there's a third one that we'll bring up here. Again, let's use our direct substitution property. See what happens? If I plug in a 0 everywhere I see an h, I would have the square root of 9 minus 3 divided by 0. That's going to give me 3 minus 3 divided by 0. And so we get 0 divided by 0, as you probably suspected, right? This is the entire video is about the 0 over 0 case and trying to figure out what algebra do I use to try to get those zeros to cancel. All right, so in this case, when you have a square root and another term here, I'm naturally thinking about conjugates, right? For some reason, with these square roots and the other term, conjugates come to mind. So what happens if we multiply by a conjugate? And the claim is this is a good technique that will help us simplify this down. So let's go ahead, and I'm going to multiply by the conjugate, square root of 9 plus h plus 3. And of course, if you multiply by the conjugate in the numerator, you probably should also do it in the denominator, so that way you're not kind of fundamentally changing anything. Okay, and let me make sure, I'm going to include the parentheses here, which just remind me that I need to distribute this multiplication, right? I need to FOIL it out. So the limit as h goes to 0. And okay, so if I was to do my firsts, so let's see, the square root and the square root should cancel out, and that would give me the 9 plus h. Let's see, if I was to do inners, that would give me negative 3 root 9 plus h. Outers, that would give me plus 3 root 9 plus h. And lasts, negative 3 times positive 3 should be negative 9. And notice, this will always happen when you multiply with a conjugate. Those inners and those outers are opposites, right? We have negative 3 root 9 plus h and positive 3 root 9 plus h. So because they're opposites, they cancel out and they sum to 0. Notice that we also have 9 and negative 9. So actually a lot of good things are happening here. So okay, I'm going to go ahead and distribute out that numerator. The denominator I'm going to leave just as is for the time being. There we go. And let me write one more line so we can clearly see what comes next. So all that's left, right, the 9's canceled out, these negative 3 and positive 3 roots canceled out. All that's left on top is the h. And then in the bottom we have this h times root 9 plus h plus 3. And so now it's kind of clear that there's the h on top and the h on bottom, and those cancel out. And so that was kind of the problem, right? This was the 0 bit, right? When you plugged in 0 for h, that's kind of what gave us the 0 over 0. So now we have the limit as h goes to 0 of just 1 divided by root 9 plus h plus 3. Let's see what happens. If I plug in a 0 everywhere I see an h, I'm going to get 1 divided by root 9 plus 3. That's going to be 1 over 3 plus 3 is 6. So in this case, my limit evaluates out to be 1/6. So here's how we can use kind of the algebra from back in the day, right? Factoring, multiplying by a conjugate, getting common denominators to help us evaluate out these limit problems. All right, so that's the big stuff for this section, section 6. I have one more video for you guys going over inequalities, and actually we have one more kind of big theorem which we'll cover called the squeeze theorem. So look forward to that in the next video. I'll see you then.